When we're studying continuous functions, it's often important that we just know certain equations or functions that we come across are continuous. And so in this lesson, hopefully we've already tried to point out many of the common functions we work with, like polynomials, radicals, trigonometric functions, logarithmic functions, all the common ones we've learned in our pre-calculus and algebra classes are graphs that are continuous as long as we are within the domain of the function. So we know some functions like square root functions aren't defined for all values of x, but as long as we are within the domain where they are defined, the graph is continuous. We don't see single pinholes in graphs. We don't see other strange behavior like we sometimes have been drawing in our examples involving limits. So it's important that we know that all of those common functions are continuous. But now what happens if I combine two or more functions that I already know are continuous? And this page here and the ones that follow, we're going to examine that a little more carefully. But this first example would be, how is it if I combine two functions? How does it turn out as far as the continuity goes? Well, let me make an example here and say, what if I had the function y equals x squared that I know the graph is continuous, it's a parabola. And what if my second function was g of x, and let's say it was the sine function, and we know that one's continuous too. That's the one where the graph just goes up and down like this, on and on like that. And like I said, y equals x squared, we know that draws the parabola, okay? Both those draw continuous functions. So in a couple instances here, what if I combine these by adding and made a function like x squared plus sine x? The theorem here says if I add, well, or subtract two continuous functions, it makes another continuous function. That's item number 2. With the other one, maybe I can make another one. This time I'm going to multiply them together, like x squared times sine x. And item number 3 says, by multiplying two continuous functions, I again get a continuous function. So even though I might have no idea what the graph of these now look like when I combine them this way, I still know it's going to be continuous. The third maybe would be, what if I divided? And this time I'm going to divide sine of x by x squared. And this time, the theorem says, okay, that's going to be continuous also, with this one exception. It's going to not be continuous when the denominator expression is equal to 0. So in the one I can see that if I'm dividing by x squared, if x were to be replaced with 0, I would be dividing by 0, and that would be what's mentioned up there. So this is continuous everywhere except at 0. Okay, so it's continuous everywhere x is not 0, but it is continuous everywhere else. Okay, and then this last theorem here, this little separate, is talking about a composition. So maybe I'll squeeze this something like that over here, number 4, and say, what if I took y equals and maybe made the sine of x squared? So what that means is we're going to apply a number and square it, and then after I've squared it, then I'm going to take the sine of that new number, and this theorem says this is going to be continuous also, because since x squared is continuous at every number, meaning I give any number I want to this inner part, I'm going to get another number out. And I know that the sine function is continuous at any number that might produce. So therefore, this new expression is going to be graphing a continuous function also. So we'd like to just use this now to examine a couple new functions that I would have created. And it's going to ask, define the intervals on which the function is continuous. Okay. Remember, the number one time a function is not continuous is when it's not defined. So as I look at number 1, I might ask myself, is this function ever not defined? Well, when I'm looking at expressions like these, when there's a fraction, I usually want to then just ask, the only time it would not be defined is if it ends up having to divide by 0. So since the denominator is x squared, you might ask, can x squared plus 1 ever equal 0? If it can, that would be a place where it's discontinuous, right? So, but I do a little careful looking, and it would imply that x squared equals -1, and assuming we're not going to go into the imaginary numbers or anything, this has no solution here. And if that has no solution, that implies that this expression is never going to be undefined, and that means the domain of this function is all real numbers, which means it is also continuous for all real numbers. So this is continuous. I like to use it as x is between -infinity and +infinity, or we could just use the interval notation and write it like this. Okay, so this one is continuous everywhere. It's continuous from -infinity to infinity. I have one more we're going to check out, or actually two, so we'll look at this one also. I want to think of it in two parts, the expression e to the x, and then separately, the square root of x minus 4. Now, we might be familiar with just y equals e to the x. It is a exponential function. We remember the graph kind of is the one that kind of does this. It is continuous everywhere. Okay, no, it doesn't have any holes, no vertical asymptotes, nothing like that. However, this one is a square root, and we remember that what we have under the square root has to have certain property to it, otherwise we cannot evaluate it, and that is what's under here must be positive or it must be 0. So we could express that by saying x minus 4 has to be greater than 0 or equal to 0, and by closer inspection to that, it is saying that x must be 4 or bigger. And that really would become the domain of this function, and whatever the domain is, that's also where it's continuous. And so we're going to say this is continuous on the interval 4 to infinity, or we could write it like this: x is greater than or equal to 4 and less than infinity. Either way, that is the interval where it is continuous. I encourage you to pause the video at this point and try and come up with an interval or intervals for this third one before I talk about it. Okay, well, if I'm looking at number 3, there is a square root again, and we know that has to be, the expression under it has to be greater than or equal to 0. So you might start by noting that x plus 3 has to be greater than or equal to 0, meaning that x has to be greater than or equal to -3. However, we also have to divide by x, and we cannot divide by x if x is 0. So my other restriction is x cannot be 0. Now that brings up a bit of a problem because 0 is within this interval of all numbers greater than or equal to -3. So what we're going to have to do is break this into two intervals. We'll start with the numbers that are greater than or equal to -3, but less than 0. And then at the same time, we'll take all the numbers greater than 0 and go from there to forever. So I say we have two intervals. One looks like this. We don't include the 0. And then we have another one, again, not including the 0. I should have said that over there. To infinity. This would be the intervals.